Okay, anyway, almost all of you enjoyed the vacation or not? The break. Say yes or no.
Yes, sir.
Yes.
Yes, sir.
Yes.
Yes, sir.
It was a very short break.
Huh? Uh, See, only for you, yeah. I think for me, I have no break. See, so you are conducting a exam for your seniors, the second and third year students. You have always the duty. Okay, but anyway, almost all of you enjoyed. Once again, I go to say happy new year to all. Okay, I think hope the this year definitely will come soon to that KTR campus. Okay. Yes.
Yes, sir.
Yes, sir.
Yes. 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 Okay. Okay. Okay, ma. I think. See, this is a continuation of the previous lecture. That is a 2 point and the 4 point probe methods. Yeah, I think already we discussed the 2 point probe technique. That how you go to measure the voltage and current by using the normal multimeter. That is a two probe. Okay, now we'll go to take the 4 probe technique here. Okay, see. Uh, okay, first I go to take this one. Yes, the screen is visible. Yeah, please confirm.
Yes, sir.
Yes, sir.
Yes, yes,
Yes, sir.
yes,
Yes, sir.
yes. Okay, okay. See, the 4 probe. I think already we did that experiment 4 probe method. How you go to measure the resistivity? Okay, I think have some ideas. Okay, see here, there are 4 probes. Is there? See, that is for example, from my left to right, I go to take this first probe. Okay, there is a 1, 2, 3, 4 like that. So the outer probe, that 1 and 4, is connected to the battery and connected to the ammeter. So for measuring the current, that inner probe, that in between 2 and 3, the voltmeter is connected. So that is you go to measure the potential difference or voltage. Okay, see, out of 4 probes, the 2 probes connected to for current and the remaining 2 connected for the potential difference. Okay, so the 4 equally spaced, and the important one is all the probes are equally spaced. See here, the distance between the 2 probes is s, the 1 and 2, 2 and 3 is also yes, and the 3 and 4 is also. So all the probes are equally spaced. That is very very important one. And the probes, where the probes is there, I think just below the probe. See here, the bottom of the probe, the sample will touch. So this is the given specimen or sample. Okay, so that all the probes simply they go to made up of tungsten metal, and it is supported by a spring at one end, and where to mount the sample surface without any damage of the sample surface. Please understand. See, this is the sample. You go to take the sample in any format. Okay, you go to discuss one by one, whether it is spherical or hemispherical or bulk material or a thin film. Okay, for different cases, you go to measure the different techniques. But anyway, there are 4 probes you go to see here. Then, if you go to measure the voltage here, see in the in between the 2 and 3. So now you tell me what is the distance between this. So this is equally spaced. There is no problem. Yes, but with respect to the first probe, the second probe starts at S. Okay, and the third probe they go to end at the distance here is S plus S 2S. So the probe, the 2 and 3 is in between the distance S and the 2S. Is it correct? Do you understand what I'm telling? Say yes or no. Yes.
Yes, sir.
Yes. So for example, in the in between the probes 2 and 3, and the limits is the starting point. That is a limit. The lower limit is yes. Upper limit is 2s. Are you understand this? Because the next you go to do the derivation. So in the time of derivation, I go to take these limits here. The lower limit is yes. Upper limit is 2s. Are you understand this concept or not? Say yes or no. Yes.
Yes, sir.
Yes, okay, okay, okay. So now I go to take the second one. See here. Uh, so there are so many different techniques are there, ma. See, out of 4 probes. See here, the method is only is the 4 point collinear probe technique. The other one is Van der Pau technique. So both the techniques you go to discuss. So in the collinear, there are 2 different dimensions you go to see. The first one is thin material, that is a hemispherical. The second one is same hemispherical but the bulk material. So that is a bulk material. The major difference between these two, see here, there is only one slice is there, but here and there is n number of slides. Okay, having a thickness t. So that is a difference between these two diagrams. So now you go to take 2 different derivation. How you go to measure the resistivity or the resistance for these materials. Okay, the most common way is how you go to measure the resistivity of the material. Okay, and also you go to see how the probes contact with the specimen. So the first one, see here. So this is a single, the ring is, the, for example, a slice, a single slice. The second one, the same slice, and the thickness that is made up of a number of slices having a thickness T. Okay, now you go to take these two different methods, 4-point collinear probe methods for thin sheet as well as the bulk material, or the thin material and bulk material. So how you go to measure the resistivity? In the fourth method already you please remember the formula that rho is equal to V by I into 2 pi s. Or you remember this formula? I think you already did in the practical. Anyone? Say yes or no.
Yes, sir.
Yes. So now you go to derive that equation. Okay. Okay. So now simply you go to see the diagram. So please tell me. So for example, this is a spherical surface. Okay. But not completely sphere. That is a hemisphere or something. So what is the area of cross section for this one? Anyone? Whether that is 4 pi r square or 2 pi r square? Yes.
Sir, please repeat.
No, see, for example, what is the basically radius of the sphere? What is the formula? I think you know.
Sir, 4 by 3 pi r cube.
Right.
Oh, right.
That is a volume or the radius? I'm asking what is the
Sir,
area of cross section, area of cross section.
area of cross section. Okay, sir. In the sphere, area of cross section is taken as circle, sir. I think so.
Yeah,
4 pi r square.
that is okay. See, 4 pi r square means you got to take that whole sphere, but that is a hemisphere. That is half of the sphere.
Okay, sir. Are you asking surface area?
2 pi r square.
Yes, 2 pi r square. Okay, correct.
Okay, sir.
Okay. For this, that is 2 pi r square. Okay, then come to the second one. So second one. So what is the area of cross section for this one? So now the material is having a number of slices. Okay, and the overall thickness is also given. The thickness is T. So now how you go to calculate the area of cross section for this one?
2 pi RH.
Yeah, exactly correct. So instead of H, you put T here. Okay, T is the thickness. So 2 pi r is nothing but the circumference, and T is nothing but the thickness. You go to multiply the circumference and thickness, we get area of cross section. Are you understand this?
Okay, sir. Yes, sir.
Yes. Okay. So now based on this only you go to derive the equation. So that is very easy to derive the equation. Come. So the first I go to take that thin material. See here. So for example, if you go to take the thickness of T, and the material is much higher than the space between the probes, and the differential resistance. So due to this spherical portion of the current, okay, the outer probe as well as the inner probe. Outer probe you go to simply measure in the current. The inner probe only you go to measure the voltage. Okay. Now, what is the general relationship between the resistance and resistivity? I think you know. According to Ohm's law, already you know that R is equal to rho into L by A. Is it correct? Yes.
Yes, sir.
Yes. So instead of see here delta R, that is a small value, and that is equal to rho into, instead of dl, I go to take dx. So that is a variable by A. A is nothing but area of cross section. Instead of L, I put dx. That is with respect to the distance. Length is varied. Now, what is the total resistance? So what is the total resistance? Simply I go to integrate. It's some limits here. So that R is equal to that integration of the V1, V2, that rho dx by, I go to replace this A by 2 pi x square. Are you understand now? Yes? That's why I'm
Yes, sir.
asking what is that? Okay. Now, instead of that V1, V2, I go to take, already I told. So what is the in between the two probes, 2 and 3? So what is the limitations here? The probe starts at S, end with 2S. Is it correct? So just now I explained in the diagram. So all the probes are equally spaced. The in between the 2 and 3, the limit is S to 2S. Yes? Is it okay? Yes? Say yes or no? See that
Yes, sir.
I go to replace the limitation. What is the limits I go to substitute here means, and that S to 2S. So yes, the distance between the first probe and second probe. The 2S is the distance between the first probe and third probe. So in between the 2 and 3, the limitation is S to 2S. Whether are you understand this or not? That's what I'm asking.
Yes, sir.
Okay. Yes. See, for example, if I go to take the probe 1 and 2, simply I put 0 to S. Are you understand? Because starting point is 0, the end at S. So this is the second probe. Second probe where they starts S, where they go to end at up to 2S. So that is S to 2S. What about the 3 and 4? Any idea? 3 and 4 means 2S to 3S. Is it correct?
Yes, sir.
Okay. But anyway, but you need S to 2S because that inner probe only connected to voltmeter. Okay. So that resistance is nothing but the potential difference. Here I go to take S to 2S rho dx by 2 pi x square. So rho constant, 2 pi is also constant. I go to take rho by 2 pi constant outside. The remaining is dx by x square. That x square goes to numerator, you get x power minus 2. So then you go to integrate. That formula already you know. Oh, x power n plus 1 by n plus 1. So automatically you get minus 1 by x here. Is it correct? That integration. Yes. So that integration of dx by x square more, I take rho by 2 pi constant outside. The remaining term is integration of dx by x square. So that is minus 1 by x. Whether it is correct or not, please.
Yes,
Yes, sir.
sir, it's
Yes.
correct.
Then you go to substitute the limits. So already minus is there. So minus 1 by 2s. Then minus of minus plus 1 by s. What is the difference? Definitely 1 by 2s. Is it correct? Yes.
Yes, sir. Yes, sir.
Yes, sir.
So the rho by 2 pi into 1 by 2s. So this is the resistance. So based on the formula, okay, I go to substitute the value, that A value, area of cross section, integrate and substitute the limits. And finally, I get the resistance R is equal to rho by 2 pi into 1 by 2s. Now, so please, now according to the Ohm's law, but already you know that R is equal to V by I. That is a well known. But see here. So here, out of the 4 probes, see the 2 probes is connected more. So only the outer probe is connected to the current. So therefore, so definitely the resistance is reduced or increased. Please, anyone. So in this case, whether the resistance is reduced or increased.
Sir, please repeat the question, sir.
See, in the basically in the 2 point probe technique, only 2 probes is there here. We directly connect the probes to positive and negative like that. But here there are 4 probes are there. So and not
Yes,
only
sir.
and the probes are equally spaced. So due to this, okay, due to this, the almost the distance is reduced. Is it correct? The in between the
Yes,
probes.
sir. Yes, sir. Distance is reduced, so area will also reduce, and sir, it will increase.
See, R is equal to rho L by M. The leave it that area
Yes,
of
sir.
section. L is reduced. What about R?
Sir, L is reduced, so automatically A is also reduced. No, oh, sir. Sorry. It will increase. It will increase.
No, R will increase or decrease. I'm asking.
Decrease,
Resistance.
Sir, R will increase. Sir, rho L by A is formula, sir. So L will increase. So it is directly proportional to R.
See, L, I am telling the distance between the probes are decreased now. That is, L is reduced.
Yes, sir.
Automatically, R is also reduced. Yes, because R is proportional to L. Yes.
Yes, sir. Okay,
So
sir. Okay, sir. Okay, sir.
what much amount see here? Basically, that R is equal to V by I, but now that is half of the value. So that is R is equal to V by 2I. Are you understand this? So due to
Yes,
the
sir. Yes, sir.
superposition,
Sorry, sir.
due to this, yes, due to the superposition of the this current at outer space, the R value is reduced by half of the value. That is R is equal to V by 2I. So now in the above equation, I go to substitute that R is equal to V by 2I. So my left hand side is now V by 2I, right hand side is rho by 2 pi 1 by 2s. The 1 get cancelled, and I go to simply rearrange the equation. That rho is nothing but V by I into 2 pi s. Is it correct? Are you understand this? The final step?
Okay, sir. Okay,
So
sir.
the rho, the resistivity is nothing but V by I into 2 pi s. So in the bracket, the 2 pi s, all are constant. 2 pi remains constant. Yes, the distance between the probe, all the distance that E is remains constant. See here, all the probes are equally spaced. That is a very, very important one. So S remains constant. So in between any, for example, 1 2 or 2 3 or 3 4, the distance is always equal. So therefore, and the 2 pi s remains constant here. The 2 pi s is remains constant. So simply that rho is proportional to V by I. So that constant only you go to give that 0.36396 something. You remember that formula? I think for already you did the practical. The rho is equal to V by S into 0 point something. Is it correct? Please check. in the lab manual. Okay, you understand this?
Sir, it was 0.213.
Yes, yeah, 0.13. So that value is 2 pi s value. S is the distance between the two probes. S is the distance between the two probes. Okay. Yes. Understand?
Yes, sir.
Okay. So
Yes, sir.
this is the formula you go to calculate the resistivity of the material. So if you once you know the resistivity, very easy to calculate the type. For example, I go to take what type of material you go to take, whether it is a N-type material, P-type material, and the related formula is also there. Okay, based on that you go to calculate the each and every one. Okay, conductivity is also very easy to calculate. Okay, etc. etc. So this is for the first case. The second case, okay, come to the second case. The second case, see whether it is a bulk material. Okay, and the T, the thickness, for example, the thickness of the T is far less than space between the probes, that is okay. But in the second case, the T is far greater. Okay, compared to see the diagram here, go to see the second diagram. See that this is thickness, so T is far greater than S. Is it correct? Say yes. See, first case, there is no thickness. This, for example, this is only one slice, a simple slice. But in the second case, see here, there is a bulk material. The thickness is comparable to the distance between the two probes. So that's why the area of cross section is now changed. So instead of 2 pi r square or 2 pi x square, so here I go to take 2 pi x into t. So that area is 2 pi x into t. Therefore, I go to take one more derivations here. That the resistance R is nothing but again the integration of V1 to V2 rho dx by 2 pi x into t. So now I go to take that the common outside. Rho by 2 pi t is constant outside. That is a dx by x. So what is the integration of d by x? That is a log of x. Then you go to substitute that s and 2s values. So definitely you get log of 2. So the rho by 2 pi t into log 2. So that is the resistance for the second case. Any doubts here? Please, whether are you understand or not? Say yes or no.
Yes, sir.
Yes. Okay. Now again I go to substitute instead of r, that is equal to v by 2i. So both sides the 2 get cancelled. Simply the rho is nothing but 2 v by I. So simply that is pi t log 2 is also there. So that is v by I or v pi t by I into log of 2. That's all. See here, the rho is equal to v pi t by I into log 2. So this is the another one more formula for the resistance for bulk material. So here T is the thickness of the material. T is the thickness of the material. First case, so directly go to calculate. See, simply that is a 2 pi s. That is based on the distance between the probes. See, carefully listen. So that is 2 pi s. Here the s is the distance between the probes. The second case, so this is purely depends upon the thickness here, because pi that I you keep pi I and I everything remains constant log 2. So only and that depends upon thickness T. If you go take T is constant, rho is directly proportional to V. That's all. Okay. Yes. Understand?
Yes, sir.
Yes. So this is a 4-point probe method by using the collinear methods. Yeah, these are the collinear methods. Okay. The collinear methods. How you go to measure the resistivity of the material. The next one is next. You come to the next one. So this is the collinear method. So there are two cases. Whether it is a material is a thin sheets or so like that, you go to take this one. Whether the material is a bulk one, you go to take this expression. Okay. Then. To the third. So third is Van der Waals method. For example, if you go to, I go to take the specimen, you go to see here, this specimen. So this is the specimen. Compared to the length and the breadth, the thickness is too small. Are you understand? Yes? You understand what I am telling?
Yes,
See,
sir.
I go, see, for example, I go to take this is a specimen. Myself, see, this is the length and this is the breadth. So compared to the length and the breadth, the thickness is too small. Too small. Okay, that type of material goes as a thin films or thin sheet. So now you go to see here. So in order to use, where you go to use this Van der Waals method, the sample thickness is much less than the width and the length of the sample. I understand what I am telling? Say yes or no?
Yes, sir.
Yes.
Yes, sir.
So for this case, in this case, how you go to avoid the errors or how you go to reduce? the errors in the calculation, simply we go to prepare a method that is that each and every point is symmetrical, or the entire sample should be symmetrical. So it is preferable that the sample, you go to take the symmetrical position. There must also be the isolated holes within the sample also. So that is the condition. Wherever you go to take this condition, the sample thickness is far less than the breadth and length and breadth of the sample. You go to take this method here, underform method, you go to applicable, and I go to take this one. And here, all the four contacts must be located where? At the edges of the sample, there is no doubt. And the area of the contact of any individual should be at least to the order of the magnitude. Okay, so now, so you go to see the basic diagram. So this is the preferred. Simply I go to take the symmetrical position, and I go to take the contacts here. See that the four corners, I go to take the corners, but you don't take the like this. So this is the equally spaced like this, and this is also not applicable. So only you go to take the points here, the corners, exactly at the corners are like that on the surface, not inside. Okay, and the contacts are numbered from 1 to 4. For example, I go to take 1, 2, 3, 4 like that, and you go to rotate either clockwise or anti-clockwise. Most probably you go to rotate clockwise direction, and each and every time you go to measure the voltage and change the current, change the direction of the current. So that is the specialty of this method here, Vanderpump method. Okay, then I go to explain how you go to measure again the resistivity by using this method, Vanderpump method. So there are 8 different diagrams are there. You go to see one. I go to explain one by one. Then I go explain the equation, how you go to take this equation. See, the first I go to take the first diagram. Okay, so this is 1, 2, 3, 4, 5, 6, 7, like that you go to understand. So the first one, second one, you see what is the difference between the first and second one? Anyone? See the points that 1, 2, 3, 4 is symmetrical. All the cases, I go to take the point that 1, 2, 3, 4 is symmetrical position. So only you go to measure the voltage, where you go to measure the voltage and what is the direction of the current. The first case, see the current will flow from left to right. The second case, that is in the opposite direction. So the first case I go to measure the voltage V1, and second I go to measure the voltage V2. Two different. Whether V1, V2 both are same or different? Anyone? Say yes or no.
Different.
Different. Okay. Now I go to rotate this in the clockwise direction. So for example, in the first, see this first diagram, I go to rotate this clockwise. There's no doubt. Now the current is coming from top to bottom. Is it correct? Yes. Say yes or no.
Yes, sir.
The points I don't change. See again the points is here 1, 2, 3, 4 like this. See the points. Now the corresponding voltage I go to take, that is V3. Then fourth one, this is the second diagram. I go to rotate in the clockwise direction. So this second one, second one, I go to rotate. So simply now the current will flow from bottom to top, and the corresponding voltage is V4. Yes, understand? I understand.
Yes. Yes.
Yes. Okay. Now V1, V2, V3, 4. There are 4 voltage measurements. The corresponding resistivity, how you go to calculate the resistivity, that equation is given there. So this is a thin sheet. Please understand, this is a thin sheet. Okay, that the formula already we discussed. The rho A, and that is nothing but pi by log of 2. And now you go to substitute that f of A. I will explain what is f of A and f of B here. Okay, so that is both are factors. Okay, geometrical factors. I will explain why you put equation and that one for like that. And Ts is the thickness of the sample. I is nothing but the current will flow. And what about this one? So this is the average. So how many voltages you go to measure? Simply 4. V1, V2, V3, V4. You go to add all these things and divided by 4. You get the average value. So why I put negative sign here for V2 and V4? Anyone? Because
Directions are in opposite.
Yes. You reverse the direction of the currents. Very simple. See the first and second one both are same here. But V1, V2, that they see the diagram is symmetrical, but only difference is the current will flow in opposite direction. Similarly, 3 and 4 both are same, but the direction. First one is top to bottom. Second one is bottom to top. Okay, that's why I put a negative sign. So the corresponding average voltage, I go to take V1 minus V2 plus V3 minus V4 by 4. So that is the average value. Okay, in the formula. And similarly, come to the next 4 diagrams. Okay, so what is the major difference between this first diagram and fifth one? Anyone? Quickly.
Current direction.
Opposite direction.
Sir, current direction. It's opposite.
Oh, that's okay. Opposite, but that voltage, where you go to measure the voltage now? The top.
Vo-
Yes,
Voltage is at top and current
current.
is in the
Yes. So the first one, see here V1, V2, you go to measure in the bottom. But here in this case, now you go to measure the V3, that V5, V6. Anyway, the current will flow in opposite direction. See, this is from my right to left, and this is from my left to right. And similarly, again, I go to rotate in clockwise. See here, now rotate in same clockwise direction. So now the current goes to bottom to top. The corresponding voltage is V7, and I go to take this one. The sixth one rotate in clockwise direction. That is V8. The current coming from top to bottom. The position almost the same. That 1, 2, 3, 4. So now, what is for this case? For this case, what is the average resistivity? Again, the same formula: pi by log of 2 FBTS. So V5 minus V6 plus V7 minus V8 by 4I. That's all. So here, TS is nothing but the sample thickness, and F of A and F of B is nothing but the geometrical factors of the given sample. If the given sample is identical, that is symmetrical in all the position, that F of A and F of B is always equal to 1. So that is for perfect symmetry. See here, so they are related to the two resistance, that ratios QA and QB, and the corresponding value that F of A, F of B is equal to 1 for perfect symmetry. Can you understand this? Say yes or no?
Yes, sir.
Yes. Okay, now you go to calculate the average value. So now the row of A and row of B is there. So simply go to take the average, that row of A plus row of B by 2. So that is the average resistivity for the given sample. So see here, that the row average is nothing but the row of A plus row of B by 2. So these two cases. So resistivity, row of A and row AB, that is average resistivity, can be calculated by using this relation. So in the final equation, that average value is almost equal to the resistivity of the that material thin sheet, and with the less amount of error. For example, you go to reduce the error. So based on this, so what are the benefits? So here already there are so many drawbacks you discussed in the 2.4 method. No? So all that drawbacks are eliminated here. For example, first you go to measure the resistivity accurately. After that, you go to calculate the conductivity. Based on that, you go to say whether it is P type or N type. So whether you know what is the type, and very easy to calculate the density, carrier density, as well as doping level and mobility. So each and every one you go to interrelated, and very easy to calculate all these things. So that is the specialty of this method, for technique. And one more advantage is the error. So that is the error is reduced. See here. Okay, the reason why I go to take means in the forefront method, the contact and the spreading, the resistance is very low with the low voltage probes, and hence accuracy is more. So the accuracy measurement is usually very, very high. And to measure the very low resistance values for probe method, and you get the better result. So that is the reason you have to add it. See, the resistance of the probe will not be added to that of the sample being tested, and it is also uses only the 2 wires to pair. Totally you get only 4 wires. So 2 wire goes to current side and 2 wire goes to voltage side. That's all, very simple. Okay, they inject the current in the resistant, and another 2 wire you should to drop against the potential difference. So in that also we go to reduce the error. Okay. Yes. Understand or not, please?
Yes, sir.
So this is the technique. What is the advantage? For example, sometimes they are asking what is the advantage of 4 probe method instead of that over to the 2 probe method. At least you go to something here. The measurement is more accurate, and the resistance value is very, very low. So that is the reason you say the better results. Okay. So that point only you go to indicate it here. So that is the 4 probe method and the advantages. Any doubts or clarifications here, Ma, please? Anyone? Yeah.
No, sir.
Okay. Okay. I think that is this is the last one. I think. See. So sometimes they're asking separately what is the core parameter technique. So the collinear method, you go to see the two different materials. How you go to calculate that resistivity, and the third case, and that is a non-collinear. That is a bulk method, Van der Pom method. So that is a Van der Pom method. So the three methods we go to discuss here for four from collinear method, two cases, and Van der Pom method. Okay, so these are the different technique. You go to measure the resistivity of the materials. Okay. Anything else or any doubts here, please? Yes?
No, sir.
No, no. Then only I move on to the next one. Ma. Any? Whether I go to stop the share screen? Any clarifications here, please?
No, sir.
Okay, okay. Then I go to stop. So please wait. I go to share the one more screen. Please wait. Yeah. Yes. The screen is visible for you. Please confirm.
Yes,
The
sir.
screen. Yes. Okay. Okay. Okay, ma. Okay. I think almost that is a title is all effect. Whether you remember? So where you take this one, all effect. So already in the first experiment, already you measured that is Hall coefficient. Do you remember more? All of you remember this one or not? The
Yes,
Hall
sir.
coefficient. Yes. So in the experiment, you measure the Hall coefficient. So based on the Hall effect. So first, you go to see before you move on to the topic. At least you know what is the magnetic Lorentz force. I think almost you studied in the lower classes. So anyone, please. So what is the magnetic Lorentz force? Any idea? Please, anyone, at least. So what is that force here? What is the expression for that one? Any ideas? I think you studied in the lower classes, the 12th standard especially. And then the current carrying conductor kept in the uniform magnetic field. So definitely some amount of force is exerted on the current charge carriers. Okay, so due to this, some amount of force is exerted. You know whether
VBL.
B B? No, no, no. No, I'm asking. That is you're telling that is a force.
So QE plus QVB.
So that B F is equal to BQV. So that is I'm asking that is a magnetic Lorentz force. So that F is nothing but the BQV. So B is nothing but the magnetic field. Q, that is a charge, and V is the velocity of the, for example, the charge carriers. So simply electrons are moving. You say that V is the velocity, or sometimes you say drift velocity. Okay, F is equal to BQV or BEV something. So I think that you've already studied the lower classes. Okay. Based on that only go to, I will explain that all effect here. See, you go to see the diagram. So this is the specimen. See, I go to take, this is the specimen. So maybe the specimen is made up of semiconducting material, either N type or P type. Okay, so I go to take this specimen here. Okay, so there is a current carrying specimen kept in the transverse magnetic field. So what is the meaning of transverse magnetic field? Anyone? What is the meaning of transverse magnetic field? And that is a parallel to the current carrying conductor or perpendicular?
Sir, perpendicular.
Perpendicular, yes, exactly correct. Very good. Okay, so when the conductor or the specimen or piece of conductor, especially the metal or semiconductors carrying a current, and it plays in a transverse magnetic field, what happens? Okay, so before I go to take, I explain this diagram. You go to see. After that, I go to explain. So this is the diagram. You please understand. This is the specimen. So I go to take here A, B, E, F. So that is a B, E, F is the front side, and O, C, D, E. So that is the back side. Okay. Now the specimen is kept the transverse magnetic field. The B is acting along y direction, and the E, that is a, for example, current. The current is acting along this positive x direction, Ox, along Ox, along Oy, that is magnetic field. According to the Lorentz concept, the force is exerted and that is always perpendicular to both that current and magnetic field. So the force is acting along the z direction, that OZ. So due to this, what happens? For example, this specimen is made up of n-type material. I think you know the majority charge carriers are electrons. So all the electrons are drifted towards where? Along OZ. So that ABEF contains the negative charges. At the same time, the minority charge carrier, that is holes, can accumulated where? That O, C, D, G. So the back side, for example, this is a back end and this is the front end. So this is the front end ABEF. All the electrons are accumulated here and all the holes are accumulated here and separated by some distance here. So that is a potential difference is there. Potential difference. So if there is a potential difference, there is no doubt the electric field is produced. Are you understand this? Say yes or no?
Yes, sir.
Yes, that is the all effect. So that is the all effect. So due to this, the EMF is induced. So whenever, see here, the piece of conductor carrying a current is placed in the transverse magnetic field, there is no doubt the electric field is produced. Where? Inside the conductor, in a direction perpendicular to both the current as well as the magnetic field. So that phenomena only you go to say all effect. Are you understand what I am telling? Say yes or no, please. Yes?
Yes, sir.
Yes. Okay. So now you understand. See, basically, you go to see this diagram, then only you go to understand. So this is the diagram where that electrons and holes are occupied or accumulated. The ABEF and OCDG. So you go to take only these two things. So that the conventional diagram only they are given here. See, the current will flow through the strip along the direction OX. The magnetic field is acting along the direction OY. So due to this, according to that force, magnetic already told. So what is the magnitude of the force here? What is the magnitude of force? That is BQV or BEV something. And this is also in opposite direction, you put negative sign. So that's why you go to see the next slide. See here, the force. If the strip is made up of either N-type or P-type, some material, semiconducting material, definitely the charge carriers in the strip will be electrons. And the conventional current will flow along the OX and magnetic field is acting along OY. There is no doubt that the velocity of electrons and the charge of these electrons, okay, is almost the velocity is drifted. And due to this, the force is acting on the electrons due to the magnetic field. So what much amount of force is acting? That F is acting along the minus BEV, and this is acting along the OZ direction. So due to this, all the electrons to be deflected and electrons are accumulated at the ABEF. So in this position, ABEF. So in this
Sir,
position, that is front. Yes, yes. Tell me.
sir, can you explain that negative sign in force formula?
Which one? No,
Sir, minus BEV. Why is that negative?
no. That is for electrons. You put negative here. For example, that is holes means you get a positive. That's very simple. Here, that is indicates
Uh,
N-type material. N-type material. See whether it is a N-type. Whether it is P-type
okay, sir.
material.
Okay, sir.
Ah,
Okay.
okay. Now at the same time, see at the same time, the ABEF will be negative and that OCDG is positive because that is all the minority charge carriers will go to that side. So now the potential difference is established where in between the front and back, that is ABEF and OCDG. Due to this, the electric field is induced. Are you understand this? Yes.
Yes, sir.
Yes. Okay. Okay. Now, due to this electric field, also some amount of force is created. Is it correct? I think you know how you go to define electric field. Simply, the electric field is nothing but the force acting per unit charge. Is it correct? Yes. E is equal to F by Q. You remember? I think you studied. Is it correct or not? So E more electric field. How you go to define electric field? The electric field is nothing but the force acting per unit charge placed at that point. I think you remember that definition or
Yes,
not?
sir.
Ah,
Yes, sir.
that E is that E is equal to F by Q or F by E something. So here that Q is replaced by E. The negative sign indicates for Z direction. That is perpendicular to both and for electrons. So due to this, some amount of field is produced. You say that is the all electric field. So due to that electric field also some amount of force is generated. That force is given by minus EH. Are you understand? Minus EH. Is it correct? See,
Yes, sir.
E is equal to F by E, therefore F is equal to EE. Is it correct? I think you know. F is equal to EE, but negative sign indicates. That is the, according to that magnetic Lorentz force, is always in opposite, and that's a negative sign you go to put for electrons here. So now, there are two kinds of forces here. One is the force is due to the magnetic Lorentz, that is minus BeV. The other one is due to the electric field, that is EH. So both the forces are equal and okay. So definitely you go to equate the forces here. Both the forces you go to equate. So once you go to equate this one, simply that the negative sign get cancelled and EE also get cancelled. So you get EH is equal to BV. Are you understand this equation number 1? Say yes or no, please.
Yes, sir.
Yes,
Yes, sir.
Yes.
yes, sir.
Okay. So at equilibrium condition, both the forces, the first one is due to the magnetic Lorentz force, second one is due to the electric field. The two forces are there. That expression you go to equate into here, the negative sign get cancelled and E also get cancelled on both sides. So I get EH is equal to BV. That's all. That all voltage, all electric field is equal to B. It's nothing but the magnetic field, and V is the velocity of the charge carriers. I think up to this you understand. Okay. Yes. Say yes or no, please.
Yes, sir.
Yes, sir.
Yes, sir.
Yes. So next, you go to derive the expression for that Hall coefficient with the help of this EH. Okay, that I think is a derivation is there. But anyway, you go to take this derivation in the next class. Okay. Yes. It will
Okay,
take.
sir.
It will
Yes,
take
sir.
some
Okay, sir.
because there is a lengthy derivation. I will explain. I say up to the equation one. That is a basic, and you understand. So now you go to rearrange the equation and substitute something, and you go to obtain the equation for that all coefficient. Okay. Yes.
Okay, sir.
Okay, sir.
Okay. I think
Yes, sir.
up to this I go to stop now, please. Okay. Today. Any doubts here for all effect? Any doubts? The
No, sir.
definition. Okay.
No,
Okay.
sir.
Okay. Derivation we will discuss in the next class. Okay. Yes. So almost